Hello everybody. So what we're trying to do is we're trying to implement a map abstract data type, which is like a generalized array where our sort of indexes can be any type, not just integers. For simplicity's sake, for here, I'm going to assume that your keys, your indexes are strings, but the methods we'll describe will work for sort of other things here. We want to have the constant time lookup of a standard array as opposed to like the log of n time lookup that a binary search tree would have. So we want something faster than a binary search tree. We want our memory usage to be proportional to n, which is the number of keys that we've actually used here, not to like the sort of number of possible keys, because like if we're using strings, right, the number of possible keys is basically infinite, right? How many possible strings are there? There's infinity of them there. So to accomplish these sort of goals here, we're going to put sort of under the hood of our data structure an array, and we'll call the array size m. So m is the size of our array there, like that. We are given a string that we want to use as an index here. So we're going to run our string through a hash function, and the job of that hash function is to turn the string into an integer in the range of 0 to m minus 1. So the range 0 to m minus 1 is exactly the array indexes that we can use an array of size m. So then we can just use that as an array index. So basically string goes in and then array index comes out here. So this is our sort of hash function, has the job of turning strings into integers that we can use as array indexes. In order to work for this, our function has to have some important properties. So this is sort of be like the sort of template for what our our hash function will look like. Is string goes in. We're not going to modify the string, so we'll pass it by const reference, and an integer between 0 and m minus 1 comes out. M will be like a global variable, or if we're doing this as part of like a class, it'll be like a member of the class or something like that. So I'm not going to define what m is. It sort of depends on like what we're doing. I'll just sort of assume that there is a variable m that I can use. So hash function is a function that takes a string and returns an integer that we'll call like h, right? So h equals the hash of something, and that h is always in the range of 0 to m minus 1 there. The return type might not be int, but it should be some integer type, right? So in assignment 5, we'll use this uint16t as the return type, which has a range of 0 to 65,535, and we'll do that because in the assignment, m is 65,536. So this return type exactly maps to the sort of set of values that particular m allows there. But you can see other sort of like integer-like types here, like you might see long or unsigned long or something like that, but it should be some integer type there. Now, we want our m to be basically as big as is practical, but of course we have to bear in mind that m determines the size of our array. So the bigger our m is, the more memory we're using. But we always usually want it to be sort of like as big as we can make it there. But there will always be more keys than m, right? Like if you think again of like how many possible strings are there, basically infinite. Even if I pick m to be 1,000,000, there's still more strings. So that means that it's always possible that we could have two different strings, but when we run them through our hash function, they give us the same number. Like maybe you have the hash of cat, right? Ends up being equal to the hash of potato, like that, right? That's not a bug, right? It's something that's inevitable. There's always going to be more strings than whatever sort of m we pick there, so there's always going to be two strings somewhere that sort of collide. So we call this a collision here. Again, like it's not like something is wrong with our hash function if we have collisions. We'll want to obviously like minimize the number of collisions, but they're unavoidable. So we'll figure out how to handle them later, but just be aware for right now that they do exist, right? That is a thing that can happen. It's not something that is like, oh, we screwed up or anything like that. It's just the nature of what we're trying to build here. Okay, so a good hash function, we don't want to build a bad hash function, right? We want to build a good hash function, right? Has 4 properties, and those 4 properties are determinism, it should have a uniform distribution, it should have an avalanche effect, and it should have a low probability of collision. I should mention the hash functions we're building are for use in hash tables here. So there are other kinds of hash functions that you use in like, hashing passwords, or like, used in sort of Git to sort of like verify file contents and stuff. We're not interested in that, so those have other requirements. I'm not going to talk about those. These are the requirements that a hash function should have to be a good hash function for the purpose of building a hash table. So like that's what we're sort of looking at here. We'll look at these one at a time. Okay, so determinism is pretty easy. It just means that if you plug in the same string twice or more than two times, right, you always get out the same output. So mathematically, if you have two strings that are identical, then their hash values should be identical. Determinism is like a hard requirement. We can't build a hash table if hashing the same string, different times produces different array indexes. If we hash hello and it spits out 17, and then we do it again and it spits out 549, then we can't sort of like be like, oh, hello lives at array index 17 and look for it there like that. So like if you don't have determinism, then you don't have sort of a hash function like at all. If you have determinism, then you may have a hash function, but it might be like a really bad one, depending on whether or not you have the other requirements there. So that's our sort of basic requirement. The next one is we want to have a uniform distribution. So that means that all of our different m output values, right? There are m possible output values from 0 to m minus 1. Those should all occur with roughly equal probability. If we plug in like a random string, then the probability that it hashes to 0, or that it hashes to 1, or that it hashes to 2, all of those sort of probabilities should be roughly the same. Like no one particular output value should be more or less likely than any other to occur. There can be some small variations, of course, but you don't want it to be like sort of crazy different here. If we were to like plot a histogram, like a bar chart of the outputs of our hash function, so like this bar is how many times did 0 come out, and this one is how many times did 1 come out, and this one is how many times did 2 come out, and so forth, all the way up to m minus 1, right? We want it to be like roughly flat like that here. Over here, it looks like 0 didn't come out very often, 1 comes out a lot, 2 really comes out often there, and then it starts to go back down like that. So this one over here is very non-uniform because some values over here are much more common and other values are much less common there. So we want the sort of distribution to be roughly uniform. It'll never be perfectly uniform, but we want it to be like, as close as we can sort of get it there. Determinism says that if you plug in the same string twice, right, you plug in identical strings, you always get the same output here. The avalanche effect is a modification of that says if you plug in similar strings, similar but not identical strings, then you should get very different outputs. So you plug in the same string twice, you get the same output, but if you just tweak it a little bit, you should get a wildly different output here. Put another way, the avalanche effect says that the hash function should sort of magnify differences in the inputs there like that. If you want to define the avalanche effect sort of formally, it says that if you flip a single bit of the input, like in binary, right, then that will result in roughly 50% of the bits in the output being flipped there. We're not going to use that definition, but that's the sort of official definition here. Intuitively, like the avalanche effect says, if you hash the word bat and you hash the word cat, even though those are really similar, in ASCII they differ only by 1, right? They should hash to wildly different output values here. And the avalanche effect is important because a lot of times the strings we're hashing, they're not random strings. They're strings that have some similarities here. Maybe they're, people's names, or maybe they're like the names of variables in a program or something like that. So they will tend to have similarities in them, but we don't want similarities in the input strings to break the sort of uniform distribution property that we talked about earlier. And then finally, we want to have a low probability of collision. So again, collisions are unavoidable. It's not like they're, like the fact that we have collisions at all is like, oh, we screwed up or something like that. But we don't want them to be any more common than necessary. If we have a uniform distribution, then hashing a random string should produce basically a random value between 0 and m minus 1. So if we hash two strings, right, then the probability that they collide, that they give the same output value, should be 1 over m times 1 over m, or 1 over m squared. That should be roughly the probability that any two random strings will collide. If your probability is greater than that, then you screwed up somewhere, right? Like your distribution is not uniform, you don't have like a good enough avalanche effect or something along those lines. Okay, so we're going to try applying those criteria by evaluating a few sort of potential hash functions for their quality. And these are kind of roughly in order of, well, they're like basically terrible to not great. Like none of these are good. So we're going to assume that our strings are random English words. Like we just sort of opened a dictionary or a dictionary file on a computer and pulled out a random word and plugged that into our hash function. We need to know where our strings are coming from in order to evaluate like what our distribution looks like, you know, what kind of what our collisions look like. So we kind of need to know what is our source of strings here. Okay, so to start with, let's say we use our string length, right? So we're just taking the length of the string and then we're using modulo m to ensure that we get a value between 0 and m minus 1. If you do, you know, a positive value remainder m, you always get out a remainder between 0 and m minus 1. So that just sort of like serves to limit the range of the values that we get out here. So is this deterministic? If you plug in the same string twice, do you always get out the same output? Yes, right? If you plug in two identical strings, of course they will all have the same length and thus they'll hash to the same value. So that's easy, right? Do we have a uniform distribution? Now again, remember, where are we getting our strings from? We're getting them from the dictionary. So we're basically asking, is the lengths of English words uniform? And the answer is no, right? The lengths of English words are not uniformly distributed. The most common length, like the median length, right, is 8 letters, or excuse me, I guess that would be the mode if you want to use the statistical term for it. There's like 13,000 words that are 8 letters long here. There's like lots of words that are short, that are like, you know, 7 or 6 or something like that. And then the longest word is basically 23 letters long. There's nothing longer than 23 letters there, except for some like weird, you know, protein names that aren't really real words there. So we have a very non-uniform distribution if you were to plot like a graph of it there. Do we have an avalanche effect? Nope, right? So like if you just take the example I gave earlier, if we hash cat and bat, we get the same hash value. They both hash to 3. So I can make a small change to my string, and it, in fact, like not only does it not produce a big change in the output is exactly the same. So finally, do we have a low probability of collision? Well, generally speaking, if you don't have a uniform distribution and you don't have an avalanche effect, then you will end up with a high probability of collision. And in fact, all words of the same length will collide. So this one here, right, string length, terrible hash function, don't use it. Okay, right, well, let's try using some stuff actually from the string here. So let's try using the first character. So here we're going to take the first character of our string here. Now in C++, there's a little bit of weirdness, which is the char type, right? That may be signed, which means that there may be negative characters. If you give a negative character modulo m, you get a negative number out, and that would cause us problems here. So what we're doing is we're just converting it to a positive value here. So unsigned just says that this should be greater than or equal to 0, so that when I modulo m on it, I get a value between 0 and m minus 1. I don't want to get any negative numbers out of my hash functions there. Because remember, we're going to use the output of this as an array index. So is this deterministic? Yep, right? Like first character, if you have two identical strings, that means they have identical characters throughout. So of course the first characters are going to be identical, so we are deterministic. Deterministic is usually like easy to determine, right? Because as long as I'm not doing something in here where I'm accessing, like, for example, the current time, or I'm using like a random number generator, or I'm like reading from a file or something, right? As long as the stuff that I use in the function just comes from the string s and m, my thing is going to be deterministic here, with one exception that we'll see in a second here. Anyway, do we have a uniform distribution? No, right? Again, so English words only start with letters A through Z and A through Z. So in ASCII, that's 97 through 122. Or 65 through 90. And within those ranges, not all letters are equally likely, right? There's not very many words that start with Q. There's not very many words that start with Z. So if you were to like plot out a histogram of our distribution, basically there would be a spike between uppercase A and uppercase z. And then there would be another spike, not even a flat spike, right, between lowercase a and lowercase z, so something like that, something like that. And then everything else would just be zeros there like that. So the distribution would not look uniform at all. Do we have an avalanche effect? Well, let's take the example from earlier. If we do cat and bat, the ASCII values of C and B differ only by 1. So the hash of cat is just equal to the hash of bat plus 1. If two words start with the exact same letter, then they have the exact same hash there like that, right? So if A is 97, B is 98, C would be 99. These would both hash to a hash value of 99 there like that. So again, if you don't have a uniform distribution and you don't have an avalanche effect, that means you probably have a high probability of collision. All words that start with the same letter will collide. So another terrible one, right? Don't use this one. It's not a good idea. All right, what if instead of just taking one of the characters, we sum up the ASCII values of all the characters here? So here we're just doing a loop over the characters in our string and adding up all the characters into H, and then again doing a mod m here at the end to get a value between 0 and m minus 1. And again, we're doing the unsigned to ensure that we always deal with values that are greater than or equal to 0 there. So is this deterministic? Yep, right. Like as long as we sort of have two identical strings, the characters are in them will be identical, so that part is usually easy. Do we have a uniform distribution here? So here we have to kind of like approximate, right? We can't sort of say what it is exactly here. So let's take a look at the shortest and longest English words and see what we would get out here. So the shortest English words are one letter long, and the earliest such one is uppercase I, right? Just sort of like a single letter I there. So that has an ASCII value of 73. So that means if we sort of plotted out the histogram, right, the chart starts at 73, right? So it's something like that right there, like that, and then the graph like that. So there's nothing but zeros before the 73 there, like that. The longest English word is 45 letters long there, like that. It's the name of like a lung disease or something like that. If you add up the characters values, you get 4,880 here. So if we sort of drop this at 4,880 like that, everything after that is 0. Right? So this part of the histogram has like stuff in it. It probably tapers off pretty quickly towards the end there like that, but there's nothing else in there like that. So if your m is larger than 4,880, the upper end of the range over here is going to be all zeros there like that. So our range is still going to be pretty non-uniform if our m is anything larger than about 4,000 there like that. So no, we do not have a uniform distribution. Do we have an avalanche effect? Again, you can try some examples, but not really, right? Cat is just bat plus 1. Rat and tar have the same hash values because we're just adding up the characters, and it doesn't matter what order you add them in, right? Addition is like that. And it doesn't matter, if you change one character somewhere in the string, the difference between the ASCII values of B and C determines the difference between their sort of hash values there. So we have like slightly more of an avalanche effect than the previous two, but still like nothing to write home about, right? And again, if you combine the fact that we have a very non-uniform distribution with a almost complete lack of an avalanche effect, then our probability of collision is going to be pretty high for this one. Okay, what if we use the string's address here? So we can get the address of the actual string inside of it here, that is the character pointer right inside it, by using s.data. Why am I using red? I don't know, right? So s.data gives us the address of this string within memory, and then we can convert it to a number by wrapping it in unsigned there, and then do it modulo m, so that I get a value between 0 and m minus 1, right? So this is just taking like where is the string located in memory and then turning that into its hash value. So is this deterministic? No, right? This one fails on the very first test here. So I can have two strings that are both hello, lowercase hello, right? But they can have different addresses. Like there's no requirement that every copy of the string hello live at the same spot in memory. In fact, in this case, this is almost certainly going to come up as false there like that. So this is useless as a hash function, so we don't even need to look at the other properties there. Sometimes people are like, oh, can I use the address as a random value? Well, not really. Like, number one is because like it's not really random, and number two is because like it's not like it's not really like this, right? It's not like, oh, if you have hello, it always lives at the same address or something like that. Okay, so we haven't seen any good hash functions yet, but we can kind of identify like what we need to make a good hash function. So we have to incorporate all the information, like all the characters, but the length of the string here, but we also need to incorporate the positions of the characters. Like we want our C at position 0 to count differently from a C at position 10 or something like that. So we're going to look at two good hash algorithms here. We're going to look at remainder hashing, and then we're going to look at multiplicative hashing. But under the hood, they're both based on converting a string to a base 256 representation. So we'll look at that sort of first. So the goal of our base 256 conversion is to convert every string into a unique integer value there. So this is different from a hash function here. Our mapping is unique. That means there's no collisions. We can always sort of take the number and go backwards. We can convert a string into a numeric value, but we can also take a numeric value and turn it back into a string. So it's just a different way of representing a string. It's not a transformation of the stuff that's in the string here like that. Now, the problem with this is that in order for this to work, right, how many strings are there? There's unlimited. So we need numbers that are unlimited as well. That doesn't exist in sort of computers here, right? Our numerical types are always limited in their range. Int is from -2 to the 31 to +2 to the 31 minus 1. Long extends that range, but it's still sort of range limited there like that. So the thing we're going to build, you can't use it on its own. Like I'll write it in C++, but it won't actually like work because for any sort of like reasonable string, it will start spitting out values that are too big to fit in an int or too big to fit in a long. We'll have to like wrap some other stuff around it to sort of turn it into a hash function there and prevent that there. So just bear in mind that like, the code I'm going to show you will, you can try it out, but at some point it will stop working. That's not like again, that's not a bug. That's just because we're not going to use it as is. We're going to wrap it up in other stuff that will kind of do the what we want with it there. So what do I mean by base 256 conversion here? So the idea is we're going to treat the characters in our string as digits in a base 256 value. So let's review a bit about like number bases to see what we mean here. So let's say we're in base 10, which is just ordinary decimal, right? So in base 10, we have 0 through 9 as our digits, 0, 1, 2, 3, 4, 5, 6, 7, 8, and 9, right? And then our digits in a number are multiplied by increasing powers of 10. So if you take 1,428 and you are like, what's the value of that? You work from right to left. You multiply 8 by 10 to the 0. You multiply 2 by 10 to the 1. You multiply 4 by 10 squared and 1 by 10 cubed. So working right to left, increasing powers of 10. All right, what about base 2? So in base 2, which is binary, right, we only have two digits. We have 0 and 1, and we multiply them by increasing powers of 2. So if you have the binary number 1011, again, we're going to work right to left. We're going to multiply 1 by 2 to the 0, 1 by 2 to the 1, 0 by 2 squared, and then 1 by 2 cubed. Okay, what about base 16, which is hexadecimal there, like that, made famous by the, Matt Damon in The Martian, right? So our digits are 0 through 9, but we need 16 different digits here. So we have to augment that with A, B, C, D, E, and F. So A means 10, B means 11, all the way out to C meaning 15. We need 16 sort of distinct symbols for our digits here, and we multiply them by increasing powers of 16. So if you have D13F, you do F times 16 to the 0, and again, remember F means 15. 3 times 16 to the 1, 1 times 16 squared, and then D, so that would be 12, would be 13, right? D would be 13 times 16 cubed, like that. So we can sort of see the pattern, right? If you are in base K, then you need K different digit symbols, and to get the value, you're going to multiply by increasing powers of K. those two things like work together here. So like we're having our k different symbols, and we have our powers of k there like that. So like let's see if those things were different, right? So let's say we have 4 different digits, so 0, 1, 2, and 3, but we multiply by powers of 3. So we have 3, 1, 2. We're going to work again from right to left, but instead of multiplying by powers of 4, we're going to multiply by powers of 3. So we do 2 times 3 to the 0, 1 times 3 to the 1, and 3 times 3 squared, so we get a decimal value of 32. So this 312 over here means 32. The problem with this, the problem with having mismatching like this 3 there, but having 4 different digits, is there's now another way that we could write the same number. If I write 1012 and we do the same process, 2 times 3 to the 0, 1 times 3 to the 1, 0 times 3 squared, 1 times 3 cubed, we get the same number. So there's multiple ways to write the same number, and we want our mapping to be unique there. If we go the other way, right, let's say we have 4-digit symbols here. So like we have these 4 symbols we can use here, but we're multiplying by powers of 5. So now we have 312 times 5. So we do 2 times 5 to the 0, 1 times 5 to the 1, 3 times 5 squared, and we get 82, like that. Okay. Well, now the problem is there are gaps in our number line. Some numbers cannot be written at all. So 312 in this system corresponds to 82 in decimal. 313 in this system corresponds to 83 in this system. But then if our digits go 0 through 3, right? So once we go 3, we have to carry. So that sort of adding 1 to 313 carries over into the 2 there like that. So the next number is 320. But the value of 320, if you plug in over here, is 85. There is no way to write the number 84 in this system here. So that just says that like those two things have to be synced up, right? We multiply by powers of however many symbols we have there. You have to use the same number for both here. So characters in our strings are bytes, and a byte can represent a value from 0 to 255. So we have 256 different byte values there. So we're going to need to multiply the byte values, the ASCII values, by increasing powers of 256 here. So if we do hello in this system here, again, we're going to work from right to left. So we multiply the ASCII value of O times 256 to the 0, the ASCII value of L times 256 to the 1, L times 256 squared, E times 256 cubed, H times 256 to the 4th, and we get this really big number right there like that, right? What is that? That's 448 billion, something like that. This is already too big for an int. So like even with just hello, we're already sort of out of range here like that. But the point is there is a way to take this number here and turn it back into the original string there. Like each string uniquely maps to a number, and then each number uniquely maps back to a string there like that. We're iterating over the characters in reverse order here, and then summing up their ASCII values here. So here's our sort of first attempt, right? So I got my string. I'm going to have a running sum in B, and then P is like what is the power on the 256? 256 to the 0, 256 to the 1, and so forth like that. So what I'm doing is I'm going to start at s.length. Now your spidey sense might be tingling, and you're saying, wait a minute, shouldn't you start at length minus 1? Like s.length is beyond the end of the string? You're right. We're going to go I minus 1 in here so that we're not actually going to access the character beyond the end of the string there like that. We're trying to avoid some issues like with negative numbers interacting with lengths here. So like that's what we're kind of like doing in here. So same thing here. We're actually going to stop at 1 and not at 0 there. So we're decrementing I to count backwards, and then we're incrementing P like that. So we grab the character, we take our character, we multiply it by using the pow function to get 256 to the pth power, and then we increment P to move on to the next power, and sort of add that into our summation, and we return the value at the end here. Now again, this function won't work. Like even if, it's got a few problems with it that we'll fix, but even if you fix all those problems, this still won't work, and that's fine. Like that's expected here like that. Yeah, this is not intended to work. As we sort of saw here, once we sort of get above a particular limit, we start getting weird values out of it here. So 1 through 4 characters are fine, but then 5 characters and beyond, we start getting this sort of negative value here, which is negative 2 to the 31. So the problem we have here is our POW function operates on floats. So we're mixing floats with ints, and that's going to give you a bad time if you're trying to do sort of purely integer math here. Floats round very differently when they get to sort of like the extremes of their ranges. So if you have an int that gets too big, it overflows into the negative range. But if you have a float that gets too big, it will round up to positive infinity. Like floats have a notion of infinity. And when you have positive infinity as a float and you convert it back to an int, you get this weird number here like that. So we want to get rid of the POW function in here. Like that's the first thing we need to do here. So we can notice that we're basically just going from 1, which is 256 to the 0, to 256 to 256 squared. So we're not just getting random powers of 256, right? We go from one power to the next. So instead of using the POW function, we can just multiply the previous power by 256 to get to the next one here. So 1 represents 256 to the 0th power there like that. And then to get the next power, we just multiply it by 256. So we're not using the POW function anymore. We're just multiplying directly by p here. That avoids the use of the POW function there like that. Now, we can do a little bit of like our stepwise analysis on this here. We just want to count the number of additions and multiplications, and this is sort of pretty easy. I'm not counting the decrement or the subtraction. I'm just counting literal pluses and literal timeses here. So plus, I'll color like that, and times, I'll color like that. So where do we do a plus? We do it here. And where do we do a times? We do it here and here. So there are 2 multiplications per character and 1 addition per character. So our total is n additions and 2 n multiplications there. That means that our function here is running in O of n time in the length of the string. Like that right there. And we'll mention that sort of later on. That's not a problem. That's basically like a requirement for making it good, is we have to look at all the characters that we have, right? Okay. We can reduce the number of multiplications via a trick known as Horner's method here. We normally wouldn't care about like this kind of like micro optimization, but I think this one's kind of interesting. So we're going to kind of invert our calculation here. So we're going to take this sum here, and we're going to work from inside out. So we do 256 times 0 plus h times that times 256 plus e, 256 times that plus l. So we're just alternating add, multiply, add, multiply, add, multiply. So each character requires 1 addition and 1 multiplication. That gives us this version here. So again, if we sort of go through and count, where do we do additions? Just there. Where do we do multiplications? Just there. Again, I'm not counting the increment as an addition there like that. We're not going to use this code as is again, right? Like this will sort of run into overflow issues with any string longer than say 4 or 5 characters. You could, put that off for a little bit by switching to longs. Or if you want to get fancy, to unsigned longs there like that. But it's still going to happen at some point there like that. So this will just be the basis for what we're going to do next. So the first good hash function we're going to look at is called remainder hashing. So remainder hashing is pretty simple conceptually. It's just you take that base 256 number, modulo m there, and that gives you a value between 0 and m minus 1, right? Some m values work better than others for this purpose here. Good choices are prime numbers, or numbers that are like nearly prime, numbers with like not very many factors. So if you took 2 prime numbers and multiplied them together, that would probably make a sort of decent m here. Bad choices are powers of prime numbers, particularly powers of 2. That's kind of unfortunately because on a computer, like doing modulo powers of 2 is sort of fast and easy, whereas other modulos are kind of slow. But like that's kind of what we sort of have to give up here. But again, we can't just do that as is. We can't just be like, oh, base 256 of our string, and then do the modulo, right? Because the base 256 function is going to overflow and screw up at some point, and then that screwed up value will get moduloed there. So what we have to do is we have to take the modulo m and move it inside of the base 256 function, inside of the loop, so that it happens while the loop is running and not just do it like once at the end there like that. It turns out that there's a property that makes this like sort of pretty easy, which is that modulo distributes over both addition and multiplication. So distributivity you've seen before here. It just says that like if multiplication distributes over addition means that you can take this and rewrite it into this. You can move the multiplication inside of the addition there like that. So multiplication distributes over addition. Modulo distributes over both addition and multiplication. So that means we can do stuff like this. We can take a plus b modulo m and move the modulo m inside of the addition and do it first and end up with something like this. So for example, let's say that we want to do 3,167 plus 7,235 modulo 10. So you can do it two different ways here. You could do the sum first, which gives you 10,402, this value over here, and then do the modulo 10. So mod 10 is easy. You just grab the ones digit. So mod 10 is 2. So that gives you 2 there like that. Alternatively, we could do what we did up here, is we can move the modulo inside the sum here and do it first. So we do 3167 mod 10, 7235 mod 10 there. This is just 7. This is just 5. So we just end up with 7 plus 5 mod 10, 12 mod 10, which is 2, which is the same value that we got over there. So no matter which way we do it, we get the same number there like that. We have to do an extra modulo at the end here sometimes because we get a value that is greater than or equal to 10. Remember, the output of this should always be between 0 and m minus 1. We don't want to get a 10 or 11 or a 12 out of this. So if we get a 12 out, we do an extra modulo to reduce it to a 2 there. Yeah, like this just is what I said there, right? Sometimes we have to do this extra modulo at the end to sort of turn this 12 into its mod 10, which is the sort of 2 there like that. As long as we're multiplying by non-negative values, multiplication is just repeated addition. So this will also work if you replace the addition in here with a multiplication, right? You could multiply those numbers out by hand and you'd get some absolutely huge number, or you can do the modulo first and do 7 times 5, which gets you, 35. And then you get a 5 out here. So whatever this sort of product multiplies to, we're multiplying a 5 by like a 7. It's going to end with a 5, right? So we're going to get a 5 over here as well there. So even if you did it with multiplication, it would still work. So our loop inside of base 256, right, for computing h only uses addition and multiplication. So we can just put the modulo m inside the loop. Just do it on h inside of there like that. So that keeps this value in here always between 0 and m minus 1, which means we don't run into the sort of limits of what an int can hold. So that solves our overflow problem. It fixes the problem of this thing not working well there. So that is our remainder hashing function there. Remainder hashing is sort of simple enough that you can do it by hand, because you can just do the modulo like wherever, provided we pick like a reasonable m, one that's not too hard to sort of like do by hand. So let's do the hash of the word potato using m equals 10. And again, I'm doing m equals 10 because mod 10 is easy. You just grab the ones digit here. So here are the ASCII values that we care about for the string potato there. So we start with the sort of whole thing here, right, which is like the whole sort of expanded form out there like that. The first thing I'm going to do is I'm going to do the mod 10 on the ASCII values. So I'm just grabbing the ones digits of all of these and throwing away everything else. So that gives me the next step here like that. Then I'm going to do the mod 10 on 256. Now there's a useful property that powers of 256, as long as your sort of power is greater than 0, will always end in a 6. So that means there'll always be 6 mod 10. So all of these powers of 256 just become 6s, except for 256 to the 0, which is 1. So then we just multiply those, right? 2 times 6 is 12, 1 times 6 is 6, blah, 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 across like that. And again, you could add those up and do it mod 10, but let's just do another mod 10. So we'll just take the 2 and the 6 and the 2 and the 6 and get this. We add those up, we get, I think, 23. I think that's right. And then if you do one last mod 10, you just get 3 out as the hash there like that. right? So I didn't even have to break out a calculator at any point here. Any place where I'm like, oh, these numbers are too big, I don't want to add them up, I just do the mod 10, and then I'm never adding things bigger than 10 to each other there. So, like, you know, my kindergartner could probably do that there. Maybe if I gave her a little help. The other good hash function we're going to look at is called multiplicative hashing here. It's an older technique, and it uses floating point calculations here, which is a little bit weird. So it's kind of equivalent to this, right? Compute your base 256 value and call that k. And then we're going to do this sort of math gnarliness on it here. But we'll go over the elements of this like sort of one by one here. Okay, so the first thing is, what the heck is this a thing here? So a is a floating point constant that should have a lot of sort of fractional digits, right? A lot of stuff going on after the decimal place here. Usually some kind of irrational number. A good value to use is based on, this one is based on like the golden ratio. So it's the square root of 5 minus 1 divided by 2, which is approximately like 0.618. But root 5 is irrational, so that means you can spit out as many fractional digits as we need here. The purpose of multiplying k by a, where we do a times k up here, right, is to basically sort of mix up the digits, so we're getting what looks kind of like a random number here. The frac function returns the fractional part of what we give it there. So just everything to the right of the decimal point. If you give it 123.456, it gives you 0.456 here. Our k value here is always, you know, greater than or equal to 0, and a is, of course, greater than 0. So that means the input to the frac function is also greater than or equal to 0. So we don't have to worry about, like, what happens if you do it on a negative value here. So what can you get out of the frac function? Well, you can get out a 0, right? If you plug in a 0, you get out a 0, so you can get out a value between 0, but you never get out a value larger than 1. If you plug in 1.0, you get out the 0.0 part of it there. So like you get values that are greater than or equal to 0, but less than 1.0. In C++, the frac function isn't called frac. Instead, it's called std:/fmod, and it comes from the CMath header. So you'll have to hashtag include CMath, and then you'll write it like this: fmod x, comma 1 there. That's how you get the frac function. And then we multiply that by m, like that. So frac, right, gives me a value between 0 and less than 1. So then if I multiply that by m, I get a value between 0 and less than m. And then finally, these things here, these little legs, right, they round down whatever we give them to the nearest integer value here. Our hash values are always integers, right? So the last step is to turn our floating point thing into an integer value here. Everything up to this point has to be done in floating point, but at the very end, we want to turn it into an integer value here. In C++, this is called the floor function, and again, it comes from the CMath header here. So if I take a value between 0 and less than m, and I round it down, what do I get? I get a value from 0 as an integer to m minus 1, which is exactly what we want. Again, just sort of going over that, right? What is k? K is always greater than or equal to 0 and is an integer. If we multiply that by a, we get a value that is greater than or equal to 0, but now it's a floating point value. It has a fractional part there. If we take the fractional part of that, then we get a value that's greater than or equal to 0, but less than 1. We multiply that by m, which gives us a value between 0 and just less than m. And then finally, we round that down, which gives us a value between 0 and m minus 1 as an integer. Excuse me. Now, just like with remainder hashing, we need to take that stuff that we sort of wrote as if we're going to do it all at the very end and move it inside the loop here. So we need to ask of the operations that we're doing, which ones distribute? Which ones can I sort of move inside the other loop here? The multiplication by a, that obviously distributes, right? The fractional part, that distributes the same way that modulo does here. That's why it's called fmod, is because it's a fractional modulo. If you do frac a plus b, you can sort of move that inside and do the fractional part of a plus the fractional part of b, and then just like with modulo, you might have to do an extra one around it to kind of throw away any accumulated integer part there. Multiplying by m, that's just multiplication, that distributes. The last one is, does the rounding down distribute? Can we move that inside of a sum? Well, let's check. So let's say we do 123.456 plus 352.987. So again, we can do it two ways. If I add those two numbers up, I get 476.443, and then when we round that down, we get 476. Over here, I'm going to do the rounding first. So I'm going to round down 123.456, and then I'm going to round down 352.987, and then I'm going to add them up. So I'm going to add 123 plus 352, which gets 475, right? So those two numbers are not the same number. So the only thing I can't distribute is the flooring. The flooring has to happen once at the end. We can't move it inside of the loop there like that. The important part of it is that the frac distributes, because that keeps our values, like our range, sort of limited. It's limited to 0 to 1, so we don't have to worry about the overflow here. So the final version of this is this. Whoops, I screwed up here. This needs to be a float. My hash values are floats throughout the loop, and they only turn into ints once at the very end when we return them there. My bad, right? So this is the same loop as before, but in here we've incorporated all of this sort of stuff like that. So this is the bit from the original base 256 part there. Then we're multiplying by a, doing fmod for the frac, and then at the very end we multiply by m and round down there. You could do the times m inside the loop and it wouldn't break anything, but we probably gain a little bit of precision by doing it at the very end there like that. So that is how you would do the multiplicative hashing there. Anyway, to sum it up here, right, we said good hash functions need to be deterministic, have a uniform distribution, have an avalanche effect, have a low probability of collision, and so far we've built two good hash functions, remainder hashing and multiplicative hashing. So if you want, you can now look at the sort of video on assignment 5, or the sort of like thing for assignment 5 there, and see what that looks like there. Otherwise, we're going to move on next week to implementing hash tables. But that'll do it for right now. Thanks a lot for your time, everybody.